Imagine standing at the edge of a vast canyon, gazing into an abyss that stretches not just across space, but through time itself. A gap in Earth's history so profound that scientists still struggle to explain it. This is not fiction. This is not mythology. This is a real mystery written in stone across our planet. The rocks beneath your feet hold secrets. Billions of years of Earth's history captured in layers of sediment and stone. Each stratum tells a story of ancient seas, shifting continents, evolving life. But there's something wrong with this record. A chapter missing from Earth's autobiography, a period where the narrative simply stops. Scientists call it the Great Unconformity, a mysterious gap in the geological record where billions of years of Earth's history appear to have vanished without explanation. What happened during this enormous span of time? Where did these rocks go? How could entire mountain ranges, seabeds, and the evidence of perhaps billions of years simply disappear from our planet's surface? The implications are staggering. Imagine finding your family photo album with decades of pictures mysteriously cut out. Now scale that to planetary proportions. This documentary explores one of geology's greatest enigmas, a puzzle that has confounded scientists since it was first discovered over a century ago. What we know is troubling enough. In locations around the world, young rocks rest directly atop ancient ones. The problem? The rocks in between, representing hundreds of millions to billions of years, are simply gone. In the Grand Canyon, for example, 1.2 billion-year-old sedimentary rocks sit directly on 1.7 billion-year-old metamorphic basement rocks. That's 500 million years, gone without a trace. To put this in perspective, that's more than twice the time dinosaurs have been extinct, an almost incomprehensible duration of Earth's history, missing. Some scientists propose catastrophic explanations, global glaciations that scoured the planet's surface, or tectonic upheavals that recycled entire continents back into the mantle. Others suggest more gradual processes, the patient work of erosion over unimaginable timescales, or chemical dissolution that left no trace of what once existed. But these explanations create as many questions as they answer. How could such extensive erasure occur so uniformly across the globe? What secrets of ancient Earth went with it? More puzzling still, this isn't just one gap. Multiple unconformities exist in the geological record, though none quite as dramatic or widespread as the Great Unconformity. The story becomes stranger when we consider what happened after this gap. The sudden explosion of complex life forms in what we call the Cambrian explosion follows directly after this missing time. Is this merely coincidence? Or might the answers to life's great evolutionary leap be hidden within this vanished chapter of Earth's history? Tonight, we'll examine the evidence, explore competing theories, and venture into realms where science borders on speculation. We'll travel to remote outcrops, where geologists first recognized something was amiss in Earth's timeline. We'll examine microscopic clues locked within mineral structures and isotopic signatures. Most intriguingly, we'll consider whether the Great Unconformity represents not just missing rock, but missing time itself. Could there be mechanisms at work that we've yet to fully understand? Processes that don't just erase rock, but somehow compress or elongate time's passage on our planet. The answers might reshape our understanding of Earth's history and our place within it. They might even alter our conception of time itself. As we explore this ancient mystery, we'll move beyond conventional geological thinking into the realm where hard science meets the truly unknown. What if the explanation isn't just about rocks and erosion? What if we're missing something fundamental about how time and matter interact on a planetary scale? The evidence we'll examine comes from disciplines ranging from geology and paleontology to astrophysics and quantum mechanics. This is a mystery that transcends traditional boundaries between sciences. Some researchers have even proposed that this gap might hold clues to questions about our universe's fundamental nature, questions about entropy, causality, and the arrow of time itself. As we delve deeper, we'll consider what this missing chapter might have contained. Lost continents, extinct life forms, perhaps even civilizations that left no trace. That last possibility may sound fantastic, But in a mystery spanning billions of years, we must consider even the most improbable scenarios. So join us as we attempt to decipher Earth's missing years, a journey through deep time, across continents, and into the very foundations of our understanding of planetary history. This is the story of the greatest gap in Earth's timeline, the prehistoric time hole that no one can fully explain. Chapter 2. Time's Broken Record. Why should a gap in ancient rocks matter to us today? Because this isn't just about missing stones, it's about missing knowledge, missing history, missing understanding of our world's true past. The Great Unconformity represents more than an academic puzzle. It stands as a humbling reminder of how incomplete our knowledge remains, how fragile our certainties are about Earth's history. Consider what we know about our planet's past. The dinosaurs that ruled for 165 million years, the rise and fall of ancient seas, the dance of continents across the globe. Now imagine what secrets might lie hidden within a gap spanning hundreds of millions to billions of years. Entire epochs of evolution, climate shifts, and geological processes completely unknown to us. If we truly want to understand where we come from, how life evolved, how our atmosphere formed, how our planet became habitable, we cannot ignore this massive gap in our knowledge. The stakes of solving this mystery extend beyond pure scientific curiosity. They touch on fundamental questions about Earth's habitability and the conditions that allowed complex life to flourish. What if crucial events during this missing period set the stage for life as we know it? What if the key to understanding our biosphere's resilience lies buried in this lost chapter? As climate change transforms our planet today, understanding Earth's complete history becomes not just academically interesting, but potentially essential for our survival. Earth has undergone dramatic transformations before, from Snowball Earth scenarios to hothouse climates. The Great Unconformity might contain vital lessons about planetary recovery from extreme conditions. There's another reason this mystery matters. It challenges our fundamental assumptions about how science works and how knowledge progresses. Modern geology is built on the principle of uniformitarianism, the idea that the same natural laws and processes operating today have operated throughout Earth's history. But the Great Unconformity suggests something different, perhaps catastrophic events or processes unlike anything in recorded history. It hints at a planet we might barely recognize. If we've misunderstood something so basic about Earth's past, what else might we be missing? What other assumptions about our world might need revision? The implications extend to how we search for life elsewhere in the universe. If Earth's history contains such dramatic gaps and discontinuities, how might we misinterpret the geological records of other worlds? As we send rovers to Mars and plan missions to potentially habitable moons, the lessons from Earth's Great Unconformity become increasingly relevant. There's a philosophical dimension to this mystery as well. It challenges our perception of time itself, the assumption that time flows uniformly, that a billion years in the distant past is equivalent to a billion years today. What if time's flow has not been constant? What if physical processes operated differently in Earth's deep past? The Great Unconformity might be a window into such possibilities. The scientific stakes are equally profound. Resolving this mystery requires integration across disciplines that rarely interact, from quantum physics to paleontology, from cosmology to geochemistry. It demands new methodologies, new technologies, and perhaps entirely new theoretical frameworks. The Great Unconformity stands as both challenge and opportunity for scientific innovation. On a more immediate level, understanding the Great Unconformity could have practical applications for resource exploration and natural hazard assessment. If we better understand the processes that shaped our planet in its distant past, we gain insight into the distribution of mineral resources and the dynamics of geological hazards. But the greatest stake may be epistemological, concerning the very nature of knowledge itself. How do we know what we know about Earth's history? How reliable is the rock record as a planetary chronicle? If billions of years can vanish from this record, what confidence can we have in our reconstructions of deep time? The Great Unconformity forces us to confront the limits of historical knowledge. For the average person, this mystery matters because it redefines our place in Earth's story. We typically think of human history as ancient at a few thousand years, but the Great Unconformity reminds us that human civilization occupies the thinnest possible slice of planetary time, and that most of Earth's story remains untold, perhaps unknowable. This humility before time's vastness might be the most valuable lesson the Great Unconformity offers us. It reminds us how recently we arrived on the cosmic stage, and yet paradoxically, we are the first species on Earth capable of even recognizing this gap in our planet's history. We alone can wonder about what's missing, can devise methods to investigate it. This documentary is not just about rocks and time. It's about humanity's unique position as Earth's storytellers, piecing together a planetary autobiography from fragmentary clues. As we proceed, keep this in mind. We are attempting to read a book with entire chapters torn out. The challenge is not just to describe what's missing, but to understand why it's gone. Chapter 3. Before the Gap. To understand what's missing, we must first understand what remains. Our story begins in the most ancient rocks on Earth, those that formed during the Hadean and Archean eons. The name Hadean comes from Hades, the Greek underworld, reflecting what geologists once imagined this period to be: a hellscape of molten rock and toxic atmosphere, uninhabitable and chaotic. Early Earth, between 4.6 and 4 billion years ago, was indeed a world we would scarcely recognize. A planet bombarded by asteroids, its surface repeatedly melted and reformed. The oldest rocks we've found date to about 4 billion years ago, tiny crystals called zircons from Australia's Jack Hills. These microscopic time capsules suggest something surprising. Liquid water existed even then. By 4 billion years ago, Earth had developed a thin crust floating on a dynamic mantle. The first continents, small, unstable patches of land, began to form. These were not the continents we know today, but rather volcanic archipelagos and primitive cratons, the ancient stable cores around which our modern continents would eventually assemble. Life may have already emerged during this time. The evidence is controversial, but some carbon isotope patterns in rocks nearly 4 billion years old hint at biological activity. If correct, this suggests life appeared almost as soon as Earth became habitable, a fact with profound implications for the prevalence of life elsewhere in the universe. As the Archean eon progressed, 4 to 2.5 billion years ago, Earth's first major continents formed. The atmosphere contained almost no oxygen, a poisonous world for creatures like us. Instead, the air was rich in methane, carbon dioxide, nitrogen, and water vapor. The sun was dimmer then, but greenhouse gases kept the planet warm enough for liquid oceans. In these ancient seas, microscopic organisms thrived, primarily anaerobic bacteria, and eventually the first photosynthetic cyanobacteria that would transform our atmosphere. The landscape would have appeared alien, dark basaltic rocks under a rusty orange sky. No plants existed to color the land green. No animals moved across the barren surface. But beneath the waves, life was busy working its slow, transformative magic. Cyanobacteria gradually began producing oxygen as a waste product of photosynthesis. For hundreds of millions of years, this oxygen was immediately captured by iron, dissolved in the oceans, creating vast deposits of iron ore that we mine today. Only after the seas became saturated with this iron oxide did oxygen begin accumulating in the atmosphere, a transition known as the Great Oxygenation Event around 2.4 billion years ago. This was Earth's first global pollution crisis. Oxygen was toxic to most existing life forms. It triggered massive extinctions among anaerobic organisms that had dominated for 1 billion years. The oxygen revolution transformed Earth's surface chemistry. Iron-rich rocks weathered differently. New minerals formed. The planet's very skin began changing composition. During this time, the continents continued growing through volcanic activity and the accretion of island arcs. Plate tectonics had begun, though perhaps operating differently than today. By 1.8 billion years ago, Earth's first supercontinent had formed, a massive landmass geologists call Columbia, or Nuna. This was the world before the great gap in our planet's record. And then something extraordinary happened. In locations scattered across the globe, the continuous record of rock formation and deposition stops. This brings us to the Great Unconformity itself, where rocks from the early Proterozoic eon are directly overlain by much younger Cambrian rocks, with hundreds of millions to billions of years missing between them. The contact between these rock layers is often startlingly abrupt. You can place your hand on it, touching two rock layers separated by an almost unimaginable gulf of time. At Frenchman Mountain near Las Vegas, 1.7 billion-year-old metamorphic rocks are covered by 520 million-year-old Cambrian sandstones, more than a billion years, simply gone. In the Grand Canyon, this same boundary is dramatically visible. Ancient, twisted schists and gneisses overlain by flat-lying sedimentary rocks nearly 500 million years younger. When John Wesley Powell first led expeditions down the Colorado River in the 1860s, he recognized this feature but couldn't explain it. The term Great Unconformity was later coined by geologist Clarence Dutton. But what Powell and Dutton observed in the American Southwest turned out to be global in extent. Similar gaps appear in rock sequences on every continent. The timing varies somewhat from place to place, but the pattern is consistent. A significant portion of Earth's Middle Age is missing from the rock record. What makes this particularly strange is that the missing interval corresponds to a critical transition in Earth's history, from the simpler microbial ecosystems of the Proterozoic to the explosion of complex life in the Cambrian. It's as if the pivotal chapters in life's story have been deliberately removed from the book. We see the setting of the stage and we see the dramatic conclusion, but the crucial middle acts are missing. Chapter 4. First Clues in Stone. Let's examine what we actually see when we look at the Great Unconformity, not just what's missing, but what remains, the physical evidence that might help us solve this puzzle. The unconformity itself appears as a distinct boundary, often visible to the naked eye as a stark contact between very different rock types. Below, typically deformed metamorphic rocks. Above, flat-lying sedimentary layers. The rocks below are usually metamorphic or igneous, rocks formed under intense heat and pressure deep within the crust, or crystallized from magma. They represent Earth's deep basement. These basement rocks show evidence of dramatic folding, faulting, and alteration. They were clearly subject to powerful forces, the building of mountains, the collision of continents. The younger rocks above, by contrast, are typically sandstones, limestones, or shales, rocks formed by the gentle deposition of sediment in shallow seas. They represent a calmer, more stable Earth. Most tellingly, these younger rocks often begin with what geologists call a basal conglomerate, a layer containing rounded pebbles and fragments of the older rocks beneath them. This tells us something crucial. The older rocks were exposed at Earth's surface long enough to be eroded, their fragments incorporated into the first layers of the younger sequence. The contact itself is usually remarkably flat, suggesting the older rocks were eroded down to a nearly level plane before the younger sediments were deposited on top of them. Geologists call such a surface a peneplain, a landscape worn down by erosion to near base level. Creating such a surface requires extensive time and stable conditions. When we examine the youngest rocks below the unconformity and the oldest rocks above it, we can date them using radiometric techniques, measuring the decay of radioactive isotopes within the minerals. These dates reveal the magnitude of the gap. In some locations, it spans more than 1 billion years. In others, merely hundreds of millions of years. But everywhere, an enormous chunk of time is missing. One of the most puzzling aspects is what happened to the missing rock. If up to 20 kilometers of crustal material was removed, where did it go? The volume of material is staggering, enough to build mountain ranges many times larger than the Himalayas. Yet we find relatively little sediment from this period preserved elsewhere. This suggests the eroded material was either recycled back into the mantle through subduction zones, distributed so finely across the globe that we can't identify it, or removed by some process we don't yet understand. Another crucial line of evidence comes from paleomagnetic studies, measurements of the ancient magnetic field preserved in rocks. These tell us about Earth's rotation and the movement of continents. Paleomagnetic data suggest unusual continental movements during the period before the Great Unconformity, including the possibility of true polar wander, where Earth's entire crust shifts relative to the spin axis. Could such dramatic planetary reorientations be connected to the missing rock record? Some researchers believe they might, suggesting global-scale processes beyond ordinary plate tectonics. The timing of the Great Unconformity also coincides with an extraordinary period in Earth's climate history, the Snowball Earth episodes, where glaciers may have covered the planet from pole to equator. Evidence for these global glaciations comes from distinctive deposits called tillites, rocks formed from material carried by glaciers, found on multiple continents in rocks just before and after the Great Unconformity. Could ice have scoured away billions of years of Earth's history? It's an appealing explanation, but problems remain. Even the most powerful glaciers typically erode only a few kilometers of crust, not the 10-20 kilometers missing in some areas. Furthermore, glacial erosion tends to be uneven, creating characteristic U-shaped valleys and fjords. The Great Unconformity, by contrast, appears remarkably flat across vast distances. Another clue comes from what happens immediately after the gap, the sudden appearance of abundant fossils in what we call the Cambrian explosion, around 540 million years ago. Before the gap, life consisted primarily of simple, soft-bodied organisms and microbial mats. After the gap, complex animals with shells, exoskeletons, and sophisticated body plans appear almost simultaneously. This extraordinary biological revolution follows directly after the Great Unconformity. Is this merely coincidence, or might there be a causal connection? Some scientists propose that the massive erosion represented by the unconformity released crucial nutrients into the oceans, creating the conditions necessary for complex life to evolve. Others suggest more radical possibilities, that the missing interval contained evolutionary experiments that left no fossil record, or that environmental conditions during this time somehow inhibited fossilization. The mystery deepens when we look at the chemical composition of rocks above and below the unconformity. Isotopic signatures of elements like carbon, sulfur, and strontium show dramatic shifts. These chemical changes suggest fundamental alterations in Earth's carbon cycle, its ocean chemistry, and the weathering processes that break down rocks and release elements into the environment. When we examine microscopic mineral grains using advanced techniques like uranium-lead dating and hafnium isotope analysis, we find evidence of unusual crustal recycling during the missing interval. These tiny grains tell a story of continents being built, destroyed, and rebuilt, at rates potentially different from anything in Earth's more recent history. Perhaps most intriguingly, some researchers have found evidence suggesting changes in Earth's rotation rate and day length across this boundary, as if time itself flowed differently before and after the Great Gap. All these clues point to something extraordinary, not just missing rocks, but perhaps a fundamentally different Earth operating under conditions we struggle to fully comprehend from our modern perspective. But just as we begin to assemble these pieces into a coherent picture, new evidence emerges that challenges our assumptions and forces us to reconsider the very nature of time's passage on our planet. Recent discoveries in the remote wilderness of northern Canada have uncovered rock sequences that appear to preserve small fragments of the missing record, tantalizing glimpses into Earth's vanished years. These rare preservations suggest something even stranger than complete erosion, a patchwork of preservation and destruction that defies simple explanation. What force could selectively erase billions of years of history in one location while preserving it in another? And why does this pattern appear on multiple continents? As we move deeper into our investigation, we must consider increasingly radical possibilities, mechanisms beyond conventional geological understanding that might explain not just missing rocks, but missing time. The evidence we've examined so far has brought us to the edge of a profound mystery, one that forces us to question our fundamental understanding of Earth's history and perhaps the nature of time itself. Chapter 5. Conflicting Evidence. As we venture deeper into Earth's missing years, the evidence becomes more contradictory, What seemed at first a simple case of erosion has evolved into something far more complex and perplexing. Let's begin with the most troubling contradiction: the sheer scale of missing material. Geological calculations suggest up to 20 kilometers of crustal thickness vanished in some regions, far more than conventional erosion can explain. For perspective, the deepest modern canyons carved by rivers over millions of years reach depths of only a few kilometers. Even continental glaciations typically remove just a few hundred meters of material. Yet the Great Unconformity represents erosion on a scale that dwarfs anything in recent Earth history. How could such extensive removal occur without leaving more evidence of the process? Furthermore, the pattern of the unconformity itself presents contradictions. While extensive across the globe, it isn't universal. In some locations, rocks from the missing interval remain partially preserved. These preservation islands create a puzzle. If global processes like glaciation or tectonic upheaval caused the Great Erasure, why were some areas spared while adjacent regions were completely stripped? When scientists began mapping the unconformity's global distribution in detail, another anomaly emerged. The boundary's age isn't consistent worldwide. It's diachronous, meaning it formed at different times in different places. In some regions, the gap spans from 1.7 billion to 500 million years ago. In others, it represents a mere 200 million years. This variable timing challenges simple, one-event explanations. The chemistry of the rocks surrounding the unconformity presents additional contradictions. In some locations, the boundary shows evidence of intense weathering, suggesting exposure to atmosphere and water for extended periods. In other areas, the contact appears fresh, as if the younger rocks were deposited soon after the older ones were exposed. How can both extensive weathering and minimal weathering exist within the same global phenomenon? Zircon crystals, nature's most durable timepieces, add another layer to the mystery. These tiny minerals preserve isotopic signatures that allow precise dating of when they formed. Studies of detrital zircons, those eroded from original rocks and deposited elsewhere, show something perplexing. Many date from the very interval supposedly missing from Earth's record. This suggests that rocks from the gap period did exist and were eroded, but their remnants were somehow removed from the geological record, except for these resistant mineral grains. Where did all that eroded material go? If conventional geology applied, we should find massive sedimentary deposits representing the eroded material elsewhere in the world. Yet sedimentary rocks of appropriate age and volume are insufficient to account for the missing material. It's as if billions of tons of rock simply vanished from Earth. Some geologists propose the material was recycled back into the mantle through subduction, the process where oceanic plates dive beneath continental ones. But this too presents contradictions. Subduction typically leaves geochemical signatures and metamorphic belts, marking ancient subduction zones. The necessary evidence for subduction on the required scale is notably lacking. Radiometric dating methods introduce additional contradictions. Different isotopic systems sometimes yield inconsistent ages for rocks immediately above and below the unconformity. These dating discrepancies suggest either problems with our dating methods or, more intriguingly, unusual processes affecting isotopic decay rates during the interval in question. The fossil record presents perhaps the most striking contradiction. The sparse microfossils before the gap give way to an explosive diversification of complex life immediately after it. This pattern defies evolutionary expectations of gradual development. It's as if life's most important evolutionary innovations occurred precisely during the missing interval, leaving us with no record of the transition. DNA molecular clock studies compound this puzzle. These analyses suggest many animal lineages diverged long before they appear in the fossil record, precisely during the time represented by the Great Unconformity. If these molecular studies are correct, complex animals were evolving for hundreds of millions of years with no fossil evidence. But why would an entire era of evolution leave no trace? Paleomagnetic data adds yet another layer of contradiction. Measurements of ancient magnetic fields in rocks show unusual patterns during the times immediately before and after the unconformity. These patterns suggest either rapid continental movements, true polar wander, where Earth's entire crust shifts relative to the spin axis, or, most controversially, changes in the geomagnetic field's behavior itself. Some researchers have even detected anomalies in the geological record that suggest changes in fundamental physical constants. Radioactive decay rates, normally considered absolute, show subtle variations in some ancient samples. If decay rates varied in the past, our entire geochronological framework might need revision. The implications would extend beyond geology into fundamental physics. The climatic evidence surrounding the unconformity presents its own contradictions. Geochemical proxies suggest extreme climate swings, from Snowball Earth glaciations to greenhouse conditions, occurred during the missing interval. Yet the physical evidence for these climate extremes is fragmentary and sometimes contradictory. Glacial deposits appear in regions that geomagnetic evidence suggests were near the equator, a climatic impossibility under current understanding. Astronomical calculations further complicate our picture. Earth's rotation has been gradually slowing throughout geological time due to tidal interactions with the Moon. Working backward, days should have been significantly shorter during the Precambrian. Yet some sedimentary rhythmites, rocks that preserve tidal or seasonal patterns, suggest different day lengths than astronomical models predict. These contradictions force us to consider more radical possibilities. What if the Great Unconformity represents not just missing rocks, but a period when Earth's physical processes operated differently? Some theoretical physicists have proposed that fundamental constants might not be constant through cosmic time. Could Earth have experienced a period when time itself flowed differently? Recent discoveries in quantum gravity theory suggest space-time itself might have quantum properties at certain scales. Could Earth have passed through a region of space where these effects became macroscopically relevant? Such speculations may seem fantastical, but the contradictions in conventional explanations push us toward increasingly unconventional hypotheses. As we accumulate more evidence, one thing becomes clear. The Great Unconformity is not merely a gap in our knowledge. It may represent a gap in our understanding of how planetary systems operate across deep time. When science encounters boundaries to its understanding, it's worth examining what other forms of knowledge might offer. Throughout human history, myths and legends have sometimes preserved memories of real geological events. Ancient flood myths, for instance, likely record actual catastrophic floods at the end of the last ice age. Could any mythological traditions preserve echoes of Earth's missing years? While human civilization arose far too recently to directly remember the events surrounding the Great Unconformity, some of the world's oldest creation myths contain intriguing parallels to our geological puzzle. Many cultural traditions speak of previous world ages or cycles of creation and destruction. The Hindu concept of yugas describes vast time cycles, including periods of dissolution and renewal. In Hopi tradition, we currently live in the fourth world, with previous worlds having been destroyed by fire, ice, and flood. Each destruction left only a remnant of life to begin again. Ancient Greek traditions spoke of ages of gold, silver, bronze, and iron, with catastrophic transitions between them. Mesoamerican calendars tracked vast cosmic cycles, including periods of destruction and rebirth. These myths likely evolved to explain observable geological features, ancient seabeds on mountaintops, fossil shells in deserts, evidence of past catastrophes. But might some preserve dim memories of Earth's dramatic transitions? More directly relevant are the anomalous artifacts and structures that occasionally surface in scientific literature, objects allegedly found in geological contexts where they shouldn't exist. The scientific community typically dismisses these out-of-place artifacts as misinterpretations or hoaxes, yet some cases resist easy explanation and have been documented by credible observers. Reports exist of modern-looking metal objects extracted from coal seams millions of years old, of complex structures found in ancient rock formations, of advanced technologies seemingly embedded in prehistoric contexts. Most famous, perhaps, is the London hammer, a wooden-handled iron hammer found in 1936, allegedly encased in 400-million-year-old rock in London, Texas. The hammerhead shows unusual composition and minimal oxidation. Skeptics reasonably point out that the rock encasing such objects could have formed recently through natural cementation processes. Yet some cases include detailed documentation of the extraction context. In 1880, J.W. Mathers, a respected municipal water engineer, reported extracting a metal cup from inside a large chunk of coal 300 feet below ground in Illinois. His technical report included multiple witnesses. In 1852, Scientific American reported on a metallic vessel blown out of solid rock during blasting operations for the Meeting House Hill in Dorchester, Massachusetts. The rock was dated to the Precambrian. The Precambrian, precisely the era most affected by the Great Unconformity. Could these anomalies, if genuine, represent technologies from civilizations that existed during Earth's missing years? The conventional scientific response is that advanced technological civilizations could not have existed in Earth's distant past, as they would have left unmistakable geological signatures. Yet this assumes such civilizations would have followed our particular technological and industrial trajectory. Different paths of technological development might leave very different signatures. More scientifically accepted are certain geological anomalies that suggest unusual conditions during the missing interval. These include mysterious spherical objects found in Precambrian strata in South Africa. These metallic spheres, known as Klerksdorp spheres, show remarkable symmetry and curious grooves that some researchers claim could not have formed naturally. Conventional explanations attribute them to concretion processes. Similarly, the controversial Oklo nuclear reactor site in Gabon presents evidence of what appears to be naturally occurring nuclear fission reactions that took place approximately 1.7 billion years ago. While most scientists accept the Oklo phenomenon as natural, it demonstrates that unusual and highly complex processes occurred during Earth's early history, processes we're still working to fully understand. Perhaps most intriguing are microstructures discovered in ancient rocks that resemble biological forms, but appear far too complex for their geological age. These controversial microfossils sometimes display features suggesting cellular complexity that shouldn't have evolved until much later. Are these contamination, mineral formations mimicking biological structures, or something more puzzling? In 1993, researchers reported finding microscopic spiral structures in Australian rocks dated to 3 billion years ago. These structures resembled modern bacteria, but appeared in rocks far older than such complexity should exist. Similar anomalous microfossils have been reported from various Precambrian formations, often generating scientific controversy before being either debunked or tentatively accepted with revised interpretations. What if some of these controversial structures represent biological innovations that evolved during Earth's missing years, with only fragmentary evidence surviving the Great Erasure? The field of paleoclimatology offers additional anomalies. Evidence for ancient ice ages appears in equatorial regions. Tropical plant fossils appear in polar regions. Earth's climate history seems more chaotic than our models predict. These climate contradictions are particularly concentrated around the periods before and after the Great Unconformity, suggesting our understanding of Earth's climatic evolution may be fundamentally incomplete. Some researchers have even proposed that Earth's axial tilt or rotational dynamics might have been significantly different during the missing interval, producing climate patterns unlike anything in more recent geological history. Then there are the geomagnetic anomalies, evidence that Earth's magnetic field behaved differently in the distant past. Multiple researchers have documented unusual paleomagnetic signatures in Proterozoic rocks. These include evidence for rapid apparent polar wander, extreme field intensity variations, and unusual reversal frequencies, all suggesting Earth's geodynamo operated under different constraints. If Earth's magnetic shield functioned differently during the missing years, this would have profound implications for surface conditions, radiation exposure, and potentially even the course of biological evolution. Returning to mythology, many ancient traditions worldwide speak of times when the sky looked different, when different stars dominated the heavens or the sun and moon behaved differently. While most such myths likely represent cultural metaphors or attempts to explain astronomical observations, some contain details that correlate with calculable changes in Earth's orientation over vast timescales. Aboriginal Australian traditions, among the world's oldest continuous cultural memories, include star stories that some researchers suggest might preserve memories of different celestial configurations from tens of thousands of years ago. If cultural memory can preserve astronomical knowledge across such time spans, it raises the possibility that myths about world ages and cosmic cycles might contain kernels of transmitted knowledge about Earth's deeper transitions. The most extreme interpretation would suggest that Earth might have experienced periods of accelerated or altered temporal flow, times when physical processes operated at different rates than today. Such speculation ventures beyond conventional science into theoretical physics concepts like variable time dilation effects or localized alterations in space-time geometry. While mainstream geology correctly remains skeptical of such exotic explanations, the accumulation of anomalies surrounding Earth's missing years continues to challenge our understanding. As we assemble these fragmentary clues, mythological parallels, anomalous artifacts, unusual geological structures, and contradictory climate evidence, a picture emerges of an Earth perhaps fundamentally different from our current understanding. Chapter 7. When Earth Held Its Breath. The stakes of understanding Earth's missing years extend far beyond academic curiosity. If we've misunderstood such a fundamental aspect of our planet's history, what else might we be missing? Consider the implications for our models of planetary development. Every theory of Earth's evolution, from its atmosphere to its oceans to its biosphere, assumes a continuous, comprehensible progression through time. The Great Unconformity suggests something different, a discontinuity, a break in Earth's developmental narrative. This challenges our fundamental assumption of uniformitarianism, the idea that present processes explain the past. What if Earth experienced periods when different physical rules applied, when chemical reactions proceeded differently, when biological evolution followed alternative pathways? The implications for our understanding of life's evolution are particularly profound. The Cambrian explosion, the sudden appearance of complex animal life, has long puzzled evolutionary biologists. This extraordinary diversification of life forms follows directly after the Great Unconformity. If the missing interval contained crucial evolutionary developments, our entire model of life's history needs revision. Recent genomic studies suggest many animal lineages diverged long before they appear in the fossil record, precisely during the time represented by the Great Unconformity. If these molecular clock analyses are correct, complex animals were evolving for hundreds of millions of years without leaving fossils. But why would an entire era of evolution leave virtually no trace? One possibility is that conditions during the missing interval were somehow inhospitable to fossil preservation, perhaps due to ocean chemistry that dissolved shells and bones before they could fossilize. Another more radical hypothesis suggests that evolution itself might have proceeded differently during this period, perhaps at accelerated rates or following pathways unlike those we observe in more recent times. The stakes extend beyond biology into planetary science. Our models of how planets develop and maintain habitability are based largely on Earth's history, a history we now realize has a massive gap. As we search for potentially habitable worlds around other stars, we calibrate our expectations based on Earth's evolutionary trajectory. If that trajectory contained unexpected discontinuities, our search parameters may be fundamentally flawed. The implications for climate science are equally significant. Earth's climate system has experienced extreme states, from global glaciations to greenhouse conditions that seem to cluster around the time of the Great Unconformity. Understanding how our planet recovered from these extremes could provide crucial insights for addressing our current climate crisis. The missing years might contain the very lessons we most need. The geological stakes are perhaps most immediate. The processes that erased billions of years of Earth's history weren't one-time events. They represent fundamental planetary mechanisms that could recur. If we don't understand what caused such massive crustal recycling in the past, We can't accurately predict future geological evolution or assess long-term risks to human civilization. Consider, too, the philosophical implications. The Great Unconformity challenges our conception of time itself, the assumption that it flows uniformly, that a million years in the distant past is equivalent to a million years today. What if time's arrow isn't as straight as we believe? What if Earth experienced periods of accelerated physical processes or altered temporal dynamics? Recent developments in theoretical physics suggest space-time itself may have quantum properties, exhibiting different characteristics at different scales or under different conditions. Could Earth have passed through regions of space where these effects became macroscopically relevant? Could fundamental constants have varied slightly during certain periods of cosmic history? Such questions may seem speculative, but they arise directly from the contradictions we observe in the geological record. The Great Unconformity forces us to consider possibilities beyond conventional understanding. The stakes escalate further when we consider implications for our search for extraterrestrial intelligence. If advanced civilizations could have existed and disappeared during Earth's missing years, our assumptions about the rarity of intelligence need revision. Conventional wisdom holds that technological civilizations would leave unmistakable geological signatures, mining operations, manufactured isotopes, artificial structures, detectable even after billions of years. But what if the very processes that created the Great Unconformity would also erase such evidence? What if Earth has experienced cycles of intelligence that leave no trace? This possibility, while speculative, has profound implications for the Fermi paradox, the contradiction between high probability estimates for extraterrestrial intelligence and our lack of contact or evidence. Perhaps the answer isn't that intelligent civilizations are rare, but that their evidence is periodically erased by the same geological processes that created Earth's great time gap. As our investigation deepens, we must confront the possibility that the Great Unconformity represents not just missing rocks, but missing physics, processes or conditions fundamentally different from those we observe today. Recent analyses of isotopic ratios in rocks from periods immediately before and after the unconformity show subtle anomalies that some researchers interpret as evidence for different nuclear interaction rates. If true, this would challenge our most basic assumptions about physical constants. It would suggest that even the laws of physics as we understand them might have applied differently during Earth's missing years. The implications extend to our understanding of consciousness and its place in the universe. If Earth's history contains discontinuities beyond conventional explanation, might consciousness itself interact with physical reality in ways we don't yet comprehend? Some theoretical physicists have proposed that consciousness may be a fundamental property of the universe, interacting with matter in ways that occasionally manifest in macroscopic effects. While such ideas remain outside mainstream science, the persistent anomalies surrounding the Great Unconformity sometimes push researchers toward increasingly unconventional hypotheses. As we prepare to examine the most compelling theories about what happened during Earth's missing years, keep in mind what's at stake: not just our understanding of geological history, but our conception of time, physical law, and life itself. If the explanation proves conventional, massive erosion through recognized processes, then geology remains on solid ground. But if more exotic explanations prove necessary, the implications ripple across all sciences. The mystery deepens when we consider that the Great Unconformity isn't Earth's only temporal anomaly. Other smaller gaps exist in the geological record, and certain transitions appear to have occurred with suspicious abruptness. Could these represent a recurring pattern? Might Earth experience periodic resets that erase portions of its history? And if so, what mechanism could possibly account for such extraordinary planetary behavior? Recent advances in planetary science reveal that other bodies in our solar system show evidence of dramatic global transitions. Mars appears to have lost much of its atmosphere and surface water relatively abruptly. Venus shows signs of having undergone catastrophic resurfacing within the last billion years. Might similar processes, perhaps more controlled on Earth due to plate tectonics, explain our planet's missing years. The most troubling possibility is that we're missing something fundamental about how planets evolve over billions of years, that our theories of gradual, uniform change fail to capture the true nature of planetary development. What if planets, like biological organisms, undergo phases of metamorphosis, dramatic transitions that leave little evidence of intermediate states? What if Earth's missing years represent such a planetary transformation? As we move toward the culmination of our investigation, new evidence has emerged from an unexpected source, deep within Earth's mantle. Seismic imaging techniques have recently revealed structures that challenge conventional understanding. These anomalous regions, massive zones where seismic waves behave unpredictably, suggest our planet's interior may harbor relics of ancient processes, perhaps even fragments of Earth's missing history. Some researchers now propose that portions of Earth's crust weren't merely eroded during the Great Unconformity, but were driven deep into the mantle in a process more dramatic than conventional subduction. If true, this would mean parts of Earth's missing years aren't actually missing. They're preserved in the mantle, accessible only to our most sophisticated geophysical techniques. But this explanation, while intriguing, raises as many questions as it answers. What could drive such massive crustal recycling? And why would it occur during this specific period of Earth's history? The answer may lie in cosmic influences we're only beginning to understand, variations in our solar system's passage through the galaxy, encounters with unusual gravitational fields, or exposure to exotic cosmic radiation. Some astronomers have proposed that our solar system periodically passes through denser regions of the galaxy, increasing the likelihood of asteroid impacts and exposure to interstellar material. Could such cosmic cycles correspond to Earth's great geological transitions? Might our planet's missing years coincide with a passage through an unusual region of the galaxy? As we prepare to examine the most controversial theories about Earth's vanished years, we stand at the threshold of potentially revolutionary insights about our planet's true history. What we discover may transform not just geology, but our understanding of life's evolution, Earth's place in the cosmos, and perhaps even the nature of reality itself. Chapter 8. Dueling Explanations. The Leading Theories. After examining the evidence surrounding Earth's missing years, we now turn to the most compelling explanations. Three major theories have emerged, each with strengths and weaknesses, each championed by different segments of the scientific community. The first and most conventional explanation is what we might call the glacial scour hypothesis. This theory proposes that massive continental glaciations during the Neoproterozoic era physically removed the missing rock layers. Proponents point to compelling evidence of ancient global glaciations, the Snowball Earth episodes, that occurred between 720 and 635 million years ago, just before the Great Unconformity in many regions. Glaciers are powerful erosive forces. Modern ice sheets have carved deep fjords and valleys, transported enormous boulders, and reshaped entire landscapes. Scale this up to global proportions, and the erosive potential becomes staggering. The glacial theory gained momentum in 2019 when a team led by C. Brenhin Keller at Dartmouth College published research linking the Great Unconformity to Snowball Earth glaciations through uranium-led dating of zircon crystals. Their data suggested a massive pulse of continental erosion coincided with the Neoproterozoic glaciations. The timing appeared perfect. Erosion rates increased dramatically just as global ice sheets expanded. But problems remain. While glaciers can indeed erode rock, they typically remove at most a few kilometers of material. The Great Unconformity represents removal of up to 20 kilometers in some locations, far beyond what ice alone could accomplish. Furthermore, glacial erosion creates distinctive landscapes, U-shaped valleys, striations, and moraines. The Great Unconformity, by contrast, appears as a remarkably flat surface across vast distances, lacking these characteristic glacial features. The second major explanation we'll call the tectonic recycling hypothesis. This theory proposes that unusual tectonic processes during the late Precambrian led to massive crustal recycling. According to this model, the assembly and breakup of the supercontinent Rodinia between 1.1 billion and 750 million years ago created unique conditions for crustal destruction. As continental masses collided, enormous mountain ranges formed, perhaps rivaling or exceeding today's Himalayas. These highlands would have been subject to accelerated erosion, their material washing into ancient seas. Simultaneously, the pattern of continental movement created unusually extensive subduction zones, regions where oceanic crust dives beneath continental plates carrying sediments into Earth's mantle. The combination of heightened erosion and extensive subduction could have removed and recycled unprecedented volumes of crustal material. This would explain both the missing rock and the lack of corresponding sedimentary deposits elsewhere. This theory gained support from recent mantle tomography studies, essentially CT scans of Earth's interior, that revealed unusual structures deep within the mantle that may represent ancient subducted material. The tectonic hypothesis also accounts for the variable timing of the Great Unconformity around the world, as the processes of continental collision and separation would have occurred at different times in different regions. However, this explanation also faces challenges. The scale and rate of crustal recycling required exceed anything observed in more recent geological history, and some regions show the Great Unconformity in areas far from active plate boundaries of that time. The third and most controversial explanation is what we might call the cosmic intervention hypothesis. This proposes that external forces, astronomical or even exotic physics, played a role in creating Earth's missing years. Several lines of evidence suggest unusual cosmic influences during the late Precambrian. The solar system's passage through denser regions of the galaxy may have increased asteroid impacts. Earth's orbit may have experienced perturbations. Some researchers have documented evidence for major impact events during this period. While none approach the scale of the dinosaur-killing Chicxulub impact, the cumulative effect of multiple impacts could have significantly altered Earth's surface. More speculatively, some theoretical physicists have proposed that variations in fundamental physical constants might occur over cosmic timescales or in different regions of the universe. If Earth passed through a region of space with slightly different physical properties, processes like radioactive decay, chemical weathering, or even the flow of time itself might have temporarily operated differently. This might explain some of the most puzzling aspects of the Great Unconformity: the apparent acceleration of physical processes, the strange isotopic signatures, and the seemingly compressed evolutionary developments that followed. While mainstream geology remains skeptical of such exotic explanations, the persistent anomalies surrounding Earth's missing years have kept these hypotheses alive in certain scientific circles. The strength of the cosmic intervention theory lies in its ability to explain features that conventional geology struggles with: the extreme scale of erosion, the abruptness of biological innovation afterward, and certain geochemical anomalies. Its weakness is obvious. It invokes mechanisms beyond our current understanding of physics and lacks the predictive power that makes good scientific theories useful. Each of these explanations has merit, and the truth may incorporate elements of all three. The Great Unconformity may represent a perfect storm of geological, climatic, and perhaps cosmic influences converging to create a unique planetary transition. The glacial hypothesis best explains the timing and some erosional features. The tectonic hypothesis accounts for the massive material recycling and regional variations. The cosmic hypothesis addresses the more anomalous aspects. As we weigh these competing explanations, new research continues to provide fresh insights. Recent studies of mineral chemistry, isotopic signatures, and mantle structures are yielding clues that may finally solve this ancient mystery. Perhaps most significantly, advanced computer modeling now allows scientists to simulate Earth's complex systems over billion-year timescales, something impossible just a decade ago. These models suggest that periodic transitions between different stable states may be an intrinsic feature of planetary evolution, that Earth may naturally oscillate between distinct modes of operation over grand geological cycles. If this is correct, the Great Unconformity might represent not an anomaly, but a predictable phase transition in Earth's development, a planetary metamorphosis that transformed our world from its adolescence into its maturity. Chapter 9. Beyond Conventional Science. To truly understand Earth's missing years, we may need to venture beyond conventional scientific frameworks into emerging fields that bridge traditional disciplines. Recent advances in complex systems theory suggest that planets, like other complex systems, may exhibit emergent properties and phase transitions that cannot be predicted from underlying physical principles alone. Earth, in this view, is not simply a rock orbiting the Sun, but a complex self-regulating system with properties similar to living organisms, what scientists James Lovelock and Lynn Margulis termed the Gaia hypothesis. If Earth functions as an integrated system, periodic reorganizations might be expected, times when multiple subsystems, atmosphere, oceans, crust, mantle, biosphere, realign into new, stable configurations. The Great Unconformity might represent exactly such a planetary phase transition, a relatively brief but intense period of reorganization that separated two distinct modes of Earth's operation. This would explain why the unconformity coincides with so many other planetary transitions: the shift from microbial to complex life, changes in ocean chemistry, alterations in the carbon cycle, and possibly even changes in Earth's orbital dynamics. New findings in geobiology support this integrated view. Recent research has revealed how deeply microbial life influences geological processes, weathering rocks, precipitating minerals, and even affecting tectonic activity through biofilms that lubricate fault zones. If the biosphere and geosphere are more intimately connected than previously recognized, changes in one would inevitably trigger changes in the other. The Great Unconformity and the Cambrian explosion might be two faces of the same transition. Quantum biology, the study of quantum effects in living systems, offers another intriguing framework. Recent discoveries suggest biological processes like photosynthesis and enzyme catalysis exploit quantum mechanical properties in surprising ways. Could quantum effects operating across vast networks of microbial life have influenced Earth's geological processes? Might the planetary reorganization represented by the Great Unconformity involve emergent quantum properties at global scales? Such ideas remain speculative, but they highlight how our understanding of Earth's history is limited by disciplinary boundaries that nature itself doesn't recognize. Perhaps most promising are new approaches in planetary chronology. Traditional geological dating relies heavily on radioactive decay, assuming constant decay rates throughout Earth's history. But what if decay rates haven't been perfectly constant? Recent laboratory experiments have detected small variations in decay rates correlated with solar activity and Earth's orbital position. While these variations are minor, accumulated over billions of years, they could significantly affect our chronology of deep time. Some researchers now suggest our timeline of Earth's earliest history may need substantial revision. If our chronological framework itself contains errors, the apparent abruptness of transitions like the Great Unconformity might partly reflect dating inaccuracies rather than actual events. New dating techniques that rely on multiple independent chronometers are now being applied to rocks surrounding the Great Unconformity. The results suggest our timeline of the late Precambrian may indeed need adjustment. These chronological revisions don't solve the mystery of the missing rocks, but they might help explain why biological evolution appears to accelerate so dramatically after the unconformity. If the time gap is actually shorter than previously calculated, evolutionary rates wouldn't need to be quite so extreme to explain the diversity that appears in Cambrian rocks. Another revolutionary approach comes from information theory, the study of how information is stored, transmitted, and transformed in physical systems. Some theoretical physicists now propose that information may be a fundamental property of the universe, as basic as energy or matter. From this perspective, Earth's history isn't just recorded in rocks, but encoded in the information content of the entire planetary system. Even if physical rocks were removed during the Great Unconformity, information about that period might be preserved in other forms, in the genetic code of organisms, in the isotopic signatures of minerals, or in the subtle structures of Earth's mantle. This information-centered approach suggests new ways to investigate Earth's missing years, looking for encoded signals that might have survived even when the original physical medium was destroyed. Advanced computational methods like machine learning are now being applied to detect subtle patterns in geological and geochemical data that human analysis might miss. These algorithms have already identified previously unrecognized correlations between widely separated rock formations, suggesting connections across the Great Unconformity that conventional analysis couldn't detect. Perhaps most radical are emerging theories in fundamental physics that question our basic assumptions about the nature of time. Some theoretical frameworks suggest time may not flow uniformly throughout the universe. Regions near massive objects experience time dilation according to Einstein's relativity. But more exotic theories propose that temporal flow might vary in other ways over cosmic timescales or in different regions of the universe. If Earth passed through a region of spacetime with different properties during the late Precambrian, this could create exactly the kind of discontinuity we observe in the geological record. Physical processes might have temporarily accelerated or decelerated, creating a period that appears compressed or expanded compared to more recent geological time. While such ideas push the boundaries of conventional science, they arise from the persistent anomalies surrounding Earth's missing years, anomalies that conventional explanations struggle to address. As we attempt to reconcile these diverse frameworks, a new paradigm is emerging, one that views Earth's history not as a simple linear progression, but as a complex, multidimensional process with periodic discontinuities and phase transitions. In this view, the Great Unconformity isn't an anomaly to be explained away, but a window into the true nature of planetary evolution, a nature more dynamic, more interconnected, and perhaps more mysterious than we previously imagined. Chapter 10. The Truth About Earth's Missing Years. We've explored competing theories, examined contradictory evidence, and ventured into speculative frameworks. Now it's time to synthesize what we've learned and offer the most comprehensive explanation for Earth's missing years. The truth, as best we can reconstruct it, involves not one single cause, but a remarkable convergence of processes, a perfect storm of planetary transformation that occurred between 1 billion and 500 million years ago. It begins with the assembly of the supercontinent Rodinia around 1.1 billion years ago. As continental masses converged, enormous mountain ranges formed, likely dwarfing today's Himalayas in both height and extent. These highlands experienced accelerated erosion, their material washing into surrounding seas, but this was just the first stage of what would become a planetary metamorphosis. The massive continental assembly altered global weather patterns and ocean circulation. Carbon dioxide was drawn down through heightened erosion and burial of organic matter, gradually cooling the planet. By 720 million years ago, this cooling, combined with orbital variations and possibly reduced solar output, triggered the first of several global glaciations, the Snowball Earth episodes. These weren't ordinary ice ages. Evidence suggests ice sheets extended from poles to equator, covering nearly the entire planet. Temperatures plummeted. The global water cycle virtually stopped. Earth entered a deep freeze. Under these extraordinary conditions, normal erosional processes were replaced by something far more powerful. Continental-scale ice sheets, up to kilometers thick, began to move. Unlike modern glaciers, these weren't confined to mountain valleys. They covered entire continents, flowing outward from the centers of land masses, carrying immense loads of rock and sediment. The erosive power was unprecedented. In some regions, kilometers of crustal material were stripped away. But the ice alone couldn't account for the full extent of the Great Unconformity. Something else was happening simultaneously. As Rodinia began to break apart around 750 million years ago, extensive rift systems developed. Huge cracks in the continental crust where plates were pulling apart. These rifts created unstable regions where crustal blocks could subside, sometimes dropping kilometers in relatively short geological time spans. Combined with glacial erosion, this subsidence amplified the creation of the unconformity. Meanwhile, at the margins of the fragmenting supercontinent, subduction zones became particularly active. Sediment eroded from the continents was transported to these zones and recycled back into the mantle. This explains one of the great puzzles of the unconformity, where all the eroded material went. It wasn't just redistributed across Earth's surface, much of it was actually returned to the mantle. Recent seismic imaging has confirmed this, revealing anomalous structures deep in the mantle that likely represent material subducted during this period of extraordinary crustal recycling. But there's another crucial factor, one that explains the extraordinary biological transformation that followed. The repeated Snowball Earth episodes didn't just reshape the physical landscape, they radically altered Earth's chemistry. During these glaciations, normal weathering processes virtually ceased. Volcanic activity continued, however, pumping carbon dioxide into the atmosphere with no weathering to remove it. When the ice finally retreated, likely due to this greenhouse gas buildup, Earth experienced conditions unlike any before or since. Atmospheric CO2 levels were extraordinarily high. Global temperatures soared. The oceans, which had been isolated beneath ice for millions of years, were suddenly exposed to this altered atmosphere and to intense weathering from newly exposed rock surfaces. The resulting chemical reactions dramatically changed ocean chemistry. Nutrients that had been limited became abundant. Elements crucial for biological innovation, phosphorus, iron, and others, flooded into marine environments. This new chemical cocktail created the perfect conditions for evolutionary experimentation. The microscopic life that had survived through the glaciations now had resources to evolve in unprecedented directions. DNA evidence confirms this timeline. Molecular clock studies suggest many animal lineages originated during or just after the Snowball Earth episodes, even though their fossils don't appear until the Cambrian. The physical gap represented by the Great Unconformity thus corresponds precisely to the most crucial period in animal evolution, when the basic body plans and physiological systems of complex life were being established. This convergence is no coincidence. The same planetary transformation that erased billions of years of rocks also created the conditions that made our kind of complex life possible. In the most profound sense, we are children of the Great Unconformity. Without this extraordinary planetary reset, the evolutionary path that eventually led to humans might never have occurred. But there's one final piece to this puzzle, one that explains why the unconformity appears so different in different regions and why its timing varies around the world. The processes we've described, continental assembly and breakup, glaciation, subsidence, and crustal recycling, didn't happen uniformly across the globe. They occurred in pulses, affecting different regions at slightly different times. What we call the Great Unconformity is actually a composite of multiple unconformities that formed through related but distinct processes over a span of several 100 million years. This explains why dating the unconformity has been so challenging, and why no single mechanism seems adequate to explain all its features. It wasn't a single event, but a series of related processes during a period of profound planetary transition. As for the more exotic explanations involving altered physics or cosmic influences, while not necessary to explain the basic features of the unconformity, they cannot be entirely ruled out. Earth does indeed pass through different regions of the galaxy over geological timescales. The solar system does experience varying cosmic ray exposure. These factors might have contributed to or triggered some of the processes we've described. What emerges from our investigation is a picture of Earth's missing years not as a simple gap, but as a crucial transition state, a planetary metamorphosis that transformed a microbial world into one capable of supporting complex life. The rocks that disappeared carried away the record of an alien Earth, a world we would scarcely recognize. In their place emerged the foundation for our world, the stage upon which the drama of complex life would unfold. The Great Unconformity, far from being merely an absence in the rock record, represents perhaps the most important presence in Earth's evolutionary history, the transition that made our existence possible. Coda, the missing key to our existence. Evidence meter 710. As our journey through Earth's missing years concludes, we're left with a profound paradox. The very gap that has puzzled scientists for generations may hold the key to understanding our own existence. Had Earth's history proceeded without this extraordinary planetary reset, the trajectory of evolution might have been entirely different. The conditions that allowed complex animals to evolve might never have materialized. In the most literal sense, we owe our existence to this gap in the record. The Great Unconformity isn't just a missing chapter in Earth's autobiography, it's the crucial plot twist that made our story possible. This realization transforms how we view our planet's history. Earth's timeline isn't a simple linear progression, but a complex narrative with moments of profound transformation, planetary metamorphoses that separate distinct world states. As we face our own planetary crisis today, climate change, biodiversity loss, and environmental degradation, Earth's missing years offer both warning and hope. Our planet has endured and recovered from extreme conditions before. Yet the timescales of these transformations, millions to hundreds of millions of years, remind us that planetary healing operates on timeframes vastly exceeding human lifespans or civilizations. Perhaps most importantly, Earth's missing years remind us of the limits to our knowledge, that even with all our scientific advancement, fundamental aspects of our planetary history remain mysterious. This humility before the vastness of Earth's story may be the most valuable lesson the Great Unconformity offers us. We are momentary witnesses to an ongoing planetary saga, most of which unfolded long before we arrived to observe it. If you've enjoyed this exploration of Earth's deepest mysteries, subscribe to our channel for more journeys through time and space. The universe contains countless enigmas waiting to be unraveled, and together we'll continue seeking the truth behind existence's greatest puzzles.